Hello and welcome to SigmaXL video tutorials. This is part 4 of the time series forecasting with SigmaXL video group, and the focus is on the autoregressive integrated moving average model, short form ARIMA. The ARIMA model was developed by Box and Jenkins. The default automatic determination of the best model order in SigmaXL uses the stepwise method of Heidemann and Kandekar. SigmaXL supports exponential smoothing, or ARIMA. It may be useful to try both to see which one gives a better model, or use the average of the forecast from both methods. If the data has negative autocorrelation, ARIMA is recommended. If the data includes continuous or categorical predictors, use ARIMA with predictors. ARIMA assumes that the time series is stationary, that is, it has the property that the mean, variance, and autocorrelation structure do not change over time. If a time series mean is not stationary, for example trending, this can be corrected by differencing, computing the differences between consecutive observations for non-seasonal and between consecutive periods for seasonal data. For non-seasonal, this will typically involve one or two orders of differencing. This order is the integrated term lowercase d. For seasonal, this will typically involve one order of differencing. This order is the seasonal integrated term uppercase D. If the variance is not stationary, use a Box-Cox transformation. For more information about stationarity, differencing, and constant, see the SigmaXL workbook. In an autoregressive model, we forecast the variable of interest using a linear combination of past values of the variable. The term autoregressive indicates that it is a regression of the variable against itself. This is like a multiple regression, but with lagged values of yt as predictors. We refer to this as an autoregressive model of order p. In a moving average model, rather than using past values of the forecast variable in a regression, a moving average model uses past forecast errors in a regression-like model. We refer to this as a moving average model of order Q. If we combine differencing with autoregression and a moving average model, we obtain a non-seasonal ARIMA model. For seasonal, the model consists of terms that are similar to the non-seasonal components of the model. The seasonal model is ARIMA, uppercase PDQ, and combined we have ARIMA, lowercase pdq, uppercase pdq. For more information, see the SigmaXL workbook. I'll start this video by opening the dataset Monthly Airline Passengers Series G by Box and Jenkins. This is the same Series G data which was demonstrated in the previous video. It is total monthly international airline passenger data from January 1949 to December 1960. In the previous video, we addressed the increase in variance over time using a Lawn transformation. However, the data must also be differenced in order to make it stationary for ARIMA. We will now demonstrate how to manually difference the data using the difference utility. Note that differencing can also be completed automatically in an ARIMA forecast model. Click the Sheet 1 tab. Click SigmaXL, Time Series Forecasting, Utilities, Difference Data. Select Lawn Airline Passengers and click Numeric Time Series Data Y. Enter 1 for non-seasonal differencing, enter 1 for seasonal differencing. Seasonal frequency is specified as 12. Click OK. A new sheet is generated with the non-seasonal difference order equals 1 and the seasonal difference order equals 1. Now I'll redo the run chart for the difference data. This now appears to be a stationary process and can be modeled using ARIMA. I will now demonstrate automatic ARIMA forecasting. Click SigmaXL, Time Series Forecasting, ARIMA Forecast, Forecast. Select Monthly Airline Passengers and click Numeric Time Series Data Y. Select Date and click Optional Time Axis Labels. As we did in the previous video, we will specify the same withhold period of 24, which will allow us to forecast 24 months and compare to withheld actual. Select Withhold Forecast Type, multi-step ahead with prediction interval at start of withhold. Check Seasonal Frequency with Specify equals 12. Check Display ACF, PACF, LB plots, and display residual plots. To address the increase in seasonal variance over time, check Box-Cox transformation and select Rounded Lambda. We will use the default prediction interval of 95%. Click Model Options. If you wanted to manually specify either the non-seasonal order or the seasonal order, it would be done here in the Specify Model dialog. However, we will use the default automatic model selection. If you want an automatic model with preset differencing, this can be set here, but we will leave these unchecked. Click OK. Click OK again. The ARIMA forecast report is generated. The blank dots are the data values in the withhold sample, with a multi-step forecast and prediction intervals displayed at the start of the withhold sample. Note that the data has been transformed using Box-Cox, but the inverse transformation is applied to produce this chart with the original units. The initial in-sample predicted value for ARIMA starts at the 14th time period due to non-seasonal and seasonal differencing. By scrolling down, we can view the model header for this forecast report. The ARIMA model summary table tells us that the ARIMA 011011 model with no constant was automatically selected based on the AICC criterion. Seasonal frequency equals 12, and Box-Cox transformation equals rounded lambda with lambda equals 0, that is, a lawn transformation. Parameter estimates and ARIMA model statistics tables are also provided. In the ARIMA model statistics table, the number of observations is 120 because 24 observations are withheld. The degrees of freedom and model statistics are also displayed in the ARIMA model statistics table. Note that the model statistics are based on the lawn transform data, not the original data. The forecast accuracy metrics are also provided. As expected, the out-of-sample withhold multi-step ahead forecast errors are larger than the in-sample estimation one-step ahead forecast errors. Note if we were primarily interested in a short-term one-step ahead forecast, then we would have selected withhold forecast type one step ahead, and this table would show out-of-sample withhold one-step ahead forecast errors. Also note that we lose 13 observations of 120 on the in-sample since we do not have predicted values at time periods 1 through 13 due to differencing. Forecast accuracy metrics are calculated using the actual raw data versus inverse transformed forecast as displayed in the forecast chart and table, so allow comparison across all model types and transformations. The forecast table is also provided and shows the same forecast and prediction interval values displayed in the forecast chart, but it is provided for further analysis and charting. Note that this table gives the forecast period number, whereas the chart displays the date. Click on the ARIMA ACF-PACF LB sheet. The ACF-PACF residuals plots indicate that the autocorrelation has been accounted for in the model. The Young box plot confirms that no significant autocorrelation remains, so this is a good fit to the time series data. If we click on the ARIMA residual sheet, we see that the residuals are approximately normally distributed, with a roughly straight line on the normal probability plot. There are no obvious extreme outliers or patterns in the charts. Note that the residuals are based on the lawn transform data, not the original data. The ARIMA model information to the right of the plots shows the Box-Cox transformation information. The ARIMA forecast for airline passenger data gives approximately the same results as the exponential smoothing results demonstrated at the end of part 3 in this video series. In conclusion, time series forecasting can use either exponential smoothing or ARIMA. Now we'll introduce a new data set to be used in ARIMA with predictors, and we will first analyze it graphically. Open daily electricity demand with predictors -electdaily.xlsx. This is daily electricity demand in gigawatts from the state of Victoria, Australia, every day during the year 2014. Temp C is the maximum daily temperature in degrees Celsius for the city of Melbourne. Temp squared is temperature squared. Workday takes on the value 1 on workdays and 0 otherwise. This data has a seasonal frequency of 7 for observations per week. Click SigmaXL, Time Series Forecasting, Run Chart. Select Demand and click Numeric Data Variable Y. Select Date and click Optional X-axis Labels. Select Show Mean and uncheck Non-Parametric Runs Test. Click OK. A run chart of electricity demand with mean center line is produced. We can see the daily seasonality with a 7-day cycle, but there is also a summer-winter effect for heating in the winter and cooling in the summer, with the peak demand occurring mid-January, which is summer in Australia. Now, we'll explore the relationship between demand and temperature. Click the Sheet 1 tab. Click SigmaXL, Graphical Tools, Scatterplots. Select Demand and click Numeric Response Y. Select Temp C and click Numeric Predictor X1. Check Trend Line and click OK. A scatterplot of electricity demand versus temperature is produced. This shows a quadratic relationship. High temperatures in the summer cause electricity demand for air conditioning, while low temperatures in the winter causes demand for heating. I'll format the trend line. This is done by clicking the trend line, right-click, and select Format Trend Line. Select Polynomial, Order 2. The trend line is now a quadratic function. Temperature squared has been added to the data so that it may be included when we do ARIMA forecast with predictors. Now we'll explore the relationship between demand and workday. Click the Sheet 1 tab. Click SigmaXL, Graphical Tools, Box Plots. Select Demand and click Numeric Data Variable Y. Select Workday and click Group Category X1. Ensure Show Mean is checked. Click OK. A box plot of electricity demand versus workday is produced. As expected, a workday 1 has higher electricity demand than a non-workday 0. Later, Temp C, Temp squared, and workday will be included as predictors in the ARIMA forecast model. Because this is daily demand data, it has a seasonal frequency of 7 for the number of observations per week. We will confirm this graphically by running a spectral density plot. Click SigmaXL, Time Series Forecasting, Spectral Density Plot. Select Demand and click Numeric Time Series Data Y. Click OK. As expected, the detected seasonal frequency for the daily data is 7. I will now use the ACF, PACF plots for the demand data. Click the Sheet 1 tab. Click SigmaXL, Time Series Forecasting, Autocorrelation, ACF, PACF plots. Select Demand and click Numeric Time Series Data Y. Because we know our seasonal frequency is 7, enter 7 in seasonal frequency and press OK. Here we can see the 7-day seasonal pattern. Click the Sheet 1 tab. Click SigmaXL, Time Series Forecasting, Seasonal Trend Decomposition. Select Demand and click Numeric Time Series Data Y. Check Seasonal Frequency and click Select 7 Daily. Click OK. Here we have a seasonal trend decomposition plot for demand. We can see the daily seasonal effect. The smooth trend, seasonal, and remainder plots were also generated. As we've seen in the previous video, these 3 add up to the original data. Now we'll introduce ARIMA with predictors in order to analyze the demand data. The ARIMA model supports continuous or categorical predictors, similar to a multiple regression in SigmaXL. In order to provide a forecast, additional predictor values must be added to the dataset prior to running the analysis. The number of forecast periods will be equal to the number of additional predictor rows. Alternatively, the predictor values from a withhold sample may be used. If neither are provided, SigmaXL will use the last row of predictor values and compute one forecast period. For more details, see the SigmaXL workbook. Click the Forecast 2 Weeks Sheet tab in the Daily Electricity Demand with Predictors, Elect Daily workbook. We will use the ARIMA model to forecast 14 days ahead starting from January 1st, 2015, which is a non-workday being a public holiday for New Year's Day. We could obtain weather forecasts for those 14 days, but for the sake of this video, we'll keep the temperature in Celsius at 26 degrees and temp squared at 676. Click SigmaXL, Time Series Forecasting, ARIMA Forecast, Forecast with Predictors. Select Demand and click Numeric Time Series Data Y. Select Date and click Optional X-axis Labels. Select Temp C and Temp Squared and click Optional Continuous Predictors X. Select Workday and click Optional Categorical Predictors. Check Seasonal Frequency and select 7 Daily. Ensure Display ACF, PACF, and LB plots is checked, and check Display Residual plots. Click Model Options. Select Automatic Model Selection. We will use the default stepwise procedure and AICC model selection criterion. Leave Specify Non-Seasonal Differencing and Specify Seasonal Differencing unchecked. Click OK to Model Options, and OK again to the ARIMA with Predictors dialog box. The ARIMA forecast report is generated. We can see the daily predicted demand with prediction intervals. The ARIMA model summary table displays an ARIMA 212-200 model with no constant and 3 predictors, seasonal frequency of 7, and model selection criterion AICC. Because Box-Cox transformation was left unchecked in the dialog box, Box-Cox transformation is not applicable. The ARIMA parameter estimates table includes significance tests. P-values of less than 0.05 are significant and highlighted in red. All of the predictors are significant. The AR1 and MA1 terms are not significant, but they must remain in the model due to hierarchy. The ARIMA model statistics are also provided. In the forecast accuracy metrics, we can see that MASC is less than 1, so it is a better forecast than would be obtained from a naive forecast. The analysis can be rerun with a withhold sample to obtain out-of-sample one-step ahead or multi-step ahead forecast errors, but we will not do so for this video. The forecast table is also provided. These are the same forecast and prediction interval values displayed in the forecast chart, but provided for further analysis or charting. If withhold periods are specified, the withhold data will be displayed as well. The predictor values for forecast are the additional predictor X values used to obtain the 14-period forecast in the forecast table. Click the ARIMA ACF PACF LB sheet. We can see that much of the autocorrelation has been removed by the ARIMA with Predictors model, with the exception of lag 5 and 25 in the ACF. Lag 5 is in the PACF. The Young box plot shows that some significant autocorrelation still remains. The red p-values are significant at alpha equals 0.05, so the model can potentially be improved. This does not mean that the model is a bad model. It can still be very useful for prediction purposes, but the prediction intervals may not provide accurate coverage. Click the ARIMA residual sheet. Looking at the histogram and normal probability plots, there are some outliers, but smaller than would have been the case if we did not include the predictors. In the next video, these will be investigated with a control chart on the residuals. Note that the additional residual plots are provided for each predictor. This concludes Part 4 of the Introduction to Time Series Forecasting with SigmaXL video. For more videos, visit us on www.sigmaxl.com or join us on YouTube. Thank you for watching.